Today's episode of the ARC Junkies Podcast is brought to you by my friends at Outlaw Leather, a family-owned and operated company in Pasadena, Texas, who's striving to manufacture the best custom hoods and leather welding accessories right here in the USA. Each piece Outlaw is putting out is touched by human hands. The artwork, cutting, the painting, riveting, they're all performed in their shop by truly talented leather workers. Outlaw's become so popular, copycats are popping up all over the place to try and replicate exactly what they're doing. But Outlaw's the original. They can put any design, logo, name, pattern, and color scheme on your choice of leather. Just shoot an email over to info@outlawleatherllc.com and they'll get you hooked up and treat you right. Outlaw carries all the gear you need to perform your craft in the field or in the shop. They carry electrodes, tungsten, power tools, PPE, fixturing tools, apparel, and more. And they offer fast, easy shipping when you order right from their website, outlawleather.com. And as an added bonus, you can get 15% off all in-stock handmade leather goods when you use code word ARCJunkies at checkout. That's outlawleather.com. We're also brought to you by Rockmount Research and Alloys. They make the craziest welding electrodes on the planet. They violate everything we know about welding. These rods aren't meant for initial fabrication. They're specifically designed and built to excel where other rods and wires fall short, on the job site in the harshest conditions. Places where you have to weld through mud, dirt, grease, and grime, but still need to achieve a quality weld. Most companies just want to put Band-Aids on the repairs and limp their equipment to the finish line. Why not switch to Rockmount and run, and still be able to tackle your next job? Rockmount has a plethora of electrodes to choose from, so you can get the job done right the first time, every time. And right now, when you spend $250 or more at rockmountwelding.com, you can get a free 1-pound tube of Tartan AAA. See the results for yourself. Reach out to Rockmount and get a free demo and see how they can help you identify which products are right for your application. Or give their product specialist a call at 1-800-272-7637. Weld stronger so your repairs can last longer with Rockmount.
Thank you for downloading show number 284 of the ARC Junkies Podcast.
Joining me in today's episode is Teresa Melfi, a technical fellow for Lincoln Electric, and Amanda Dodge, who is an additive engineer with Lincoln Electric. Many times on this show, I have mentioned additive manufacturing, but have never been able to fully explain what it actually is. So I brought Teresa and Mandy on the show to take a deep dive into the process. Additive manufacturing isn't new, but it is an emerging technology in the welding industry and a new path for those in the industry looking to explore as a career. This technology is a game changer for our industry and has so much potential that allows us to create, design, and implement new parts and components that otherwise would have to be casted. But casting is such a long process, and sometimes you can't get the needed mechanical properties you otherwise would need. Let's go ahead and get into it. Fire up your machine, drop your hood, and turn me up 5.
You're listening to the ARC Junkies Podcast, helping you make every weld better than your last with each episode. And now your host, Jason Becker.
All right, Teresa, Amanda, thanks for coming out to the ARC Junkies Podcast.
Oh, glad to be here.
Yeah, thanks for having us.
So, Teresa, I met you on several occasions. First, over at the Weld Summit. I think you were on the podcast probably about this time last year before we kicked off the Weld Summit in August. So, welcome back to the show.
Thanks.
But I've talked about additive manufacturing several times, or I've referred to it several times on the show. But I honestly don't understand all I know about it. And so I wanted to bring some specialists onto the show to talk about exactly what additive manufacturing is. So, joining me tonight is Teresa Melfi and Amanda Dodge. So thank you both for coming on the show. So, Teresa, actually, how did you get started with Lincoln Electric? How long have you been with the company?
Mandy and I were just talking about this. In fact, I've been with the company for over 40 years now.
Congratulations.
So yeah, it's right out of university, came here, and the first thing they do with you at Lincoln Electric is they put you through welding school and you get certified. So
good move.
Yeah, that was my introduction, and that's all it took was that, and I am hooked.
Okay, Mandy, how'd you start?
Yeah, so I actually was the first intern in the additive manufacturing department back in 2019 when we got our own facility. So I was there for just the summer. I went back to school, finished my bachelor's in mechanical engineering at Ohio State, and then I've been full-time ever since then. So I'm not quite at 40 years, but I'm going on 3 now. So
Okay. Well, you got to start somewhere. Yeah.
Yeah.
So now, Teresa, has Additive Manufacturing, are you guys over in the automation sector of Lincoln still, or do you have like your own facility now?
Yeah, it's actually we have a facility. It's quite a large facility. It's got, I don't know, a couple of dozen cells in it and growing all the time.
So is that right at automation?
It's in its own facility, but we're a part of automation.
Oh, that's awesome. Yeah, because I remember touring automation before, and that's where I seen Additive Manufacturing the first time. I actually went up to the educator's workshop with Charlie Cross. He's actually the one that I recommended that I reach out and get in touch with you. But yeah, I mean, like that's where they had like all the like little laser cutting, and then they had CNC plasma cutting and the robotic cells and all that. And that's where I guess the backhoe arm was, that it was completely welded up with all the hydraulic lines internal and stuff. But they weren't doing a whole lot with it at that time, or anything that they could show us. So it's kind of cool to see this, this new technology coming to light.
Yeah, it's really taken off. The factory is about a 5-minute drive from the main campus. So we've still got all of the scientists and metallurgists and welding engineers and, that are very close by, but it's dedicated to additive manufacturing. That's pretty much, that is all you do there. Mm-hmm. Yeah. So
that's got to be nice being off the main campus, because you're not like right there in the limelight, like the top brass isn't always walking around checking on you every single minute of the day. You kind of get a little bit more time to play around and hey, let's see if this will work, or what if we try this?
And they do a lot of playing. I will say that it's always fun, because every time they get an intern in, they give them some really crazy project, whether it's building flower pots or whatever, just to make sure that they've got their hands and their minds set around what you can and can't do with this technology.
Oh, that's pretty neat. So for those that don't know, Teresa, could you explain to me exactly what additive manufacturing is?
Sure. So, additive manufacturing from a big scope is building things up layer by layer. And there's additive manufacturing of concrete, where they they normally put up forms and pour concrete for a wall. Instead, they take something that looks a lot like a toothpaste tube, and they squeeze concrete out. And they can then make whatever shape walls they want in a building. Then a lot of people through schools and makerspace and libraries know additive manufacturing of plastics, where you can build little army men and stuff out of plastics. That's moved into the metals realm, where they can do that with metals. So it's sort of size by size. So that's kind of the smaller stuff. Well, additive manufacturing, where you're using weld metal, is big stuff. 100 pounds is small. It's more like 1 ton. And it's taking weld metal and building up layer by layer. So if you think about a MIG torch, you take that and you have a computer program tell it what path you want it to take and how thick that part has to be, and you just keep building up until you've got a part there.
So 3D printing with MIG wire.
3D printing with wire, yeah, exactly.
And you've been able to do some really cool things, because like I said, I got to see your presentation up at the AISC convention, and you talked about like this boat prop that you all did that was originally, they wanted it to be done out of cast, and it just wasn't feasible, or well, it's your story. I'll let you tell it.
Do you want me to do it?
You can go for it.
So that one was a hollow bladed propeller. So it's hard to make something hollow. You can do some spin casting and things like that. I think it ended up as a nickel aluminum bronze. And if you think about a propeller blade, what we were able to do is just build up around the outside so that there was nothing in the middle. So it was kind of an oval shape that was built up. And when you watch that video, I love using that video because it's like choreography. It's like a dance between the robot and the manipulator and the wire to have everything welded, essentially, not always, but as much as possible in the downhand position, because that's where you get the fewest defects, and that's where gravity helps you. So it's just that's a really good example of a complex part that was done.
And then you were able to save the client like time and money because I guess of the casting process, and like you said, it had to be hollow. I'm guessing because of weight. It's a massive boat prop. What was the overall size of it?
The prop was probably about 15 feet in diameter. If you take both sides,
I'd probably say 5.
Oh, 5 feet for each blade?
Yeah.
Okay, 5 feet for each blade.
Okay,
so,
it's probably about like a 10-foot diameter or so.
Yeah.
That's still pretty big.
Yeah.
So how do you, like you were talking about, you said, you've got the rotator moving around, you've got the MIG gun, and the MIG gun's kind of attached to a robotic arm, and they just kind of, like you said, a choreography. It's like a dance move. They work so synergistically between the two. One part's rotating as the gun's moving the opposite direction. So I guess that's to kind of help facilitate the weld metal buildup and maintain the process and I guess travel speed, because now you're moving two different directions or opposite directions at the same time.
Yeah. So if from we're all welders, so we'll talk welding. When you're welding, if you can use gravity, it always helps you increase your deposition rate. And so you have the manipulator working, you've got the 6-axis robot working, and you also have the power source working. So you're changing things like your gun angle, your stick out, your inner pass temperature is monitored. So it's all a very very rigid way of building something up. And they've been doing this for a long time, but it hasn't really been commercially viable until the computers kind of caught up and could make all of this work together.
That was going to be another one of my questions. How long has this technology been around for use with metals? Because I've seen 3D printing for 5-10 years. Just like you said, polymers and plastics and stuff like that. Now it's become more affordable for the hobbyists and stuff. But how long have we been doing it with weld metal?
So weld metal, they called it weld metal buildup, but the first patent was in 1920.
Jeez.
And it was for 1920. Yeah, it was a Westinghouse patent for weld metal buildup to build like articles, like pictures and things like that. There was another patent in the early 60s to build pressure vessels and pressure vessel heads. So it's been in use for a long time, but the words were different. We called it weld metal. We called it weld metal buildup. We followed weld metal buildup rules, where now it's cool and trendy, and we call it additive manufacturing. But essentially, it's still the same thing. But how long is it actually? Have you been able to do this kind of manipulation and choreography kind of stuff? Probably 10 years.
Wow. When you think about it, that's not that long ago.
And it is changing so quickly. There's so much new technology out there, vision-based systems and sensor systems, and you don't even think that they would apply to welding, but all of a sudden they've got a home in this additive manufacturing.
That's pretty neat stuff. So when you get a part in, like let's say that the boat prop, for example, because everybody's familiar with it now that they've heard the story. When you get a part like that in, how do you develop a procedure for that? How do you figure out, because if I know, if I'm going to go weld on a piece of material, I need roughly 1 amp per, thousandths of material thickness, but I'm not welding on a thick part. I'm actually building the part. So how do you figure out amps, volts, wire feed speed, contact tip to work distance, work angle, travel speed, all the variables that go into it?
So there's a few different areas that go into the technology. So there's the material development, like you're talking about, the amps, the volts, all of those traditional welding parameters. So typically we start with the material we want to print with, and it kind of starts like very simply, just bead on a plate. Once you have a solid bead, then you need to stack it on top of itself, make sure that that builds nicely. You need to build the other direction for multi-bead thickness. Once you have welding procedures that are solid, that are good quality, then we have to characterize them. So figure out, you're combining different travel speeds, different amperages, like you said. What does that look like in the modeling software? So then once we get a part geometry in the door, it's if it's something complicated like a propeller where you're going out of position or using the positioner, you would start with, or as like the print engineer, I would start with the build strategy. So how do I want to print it? Can I go straight up? Do I need to manipulate it? Do I need to split it into different components? And then each component, so each program, essentially it's like slicing the part into quite like a loaf of bread. So you slice it into individual cross sections. Those would be your layers, like Teresa was talking about. And then as the engineer, you sort of have options of how you want to lay out those beads to fill in the layers. So if it's, say, just you're filling in, I don't know, a cylinder, you could either go back and forth in more of a serpentine pattern. You could do rings like a tree and more of a concentric pattern. All of those choices are sort of up to the engineer. And then all of that with the modeling that comes in from the procedure characterization, being able to see how the beads are going to be laid out in each cross section of each layer of the entire part geometry, making sure it's solid, making sure you have good overlap. All of that gets turned into essentially just a G code that the robot kind of does the hard work with and follows the G code, deposits all the beads, and then one bead at a time, one layer at a time, you end up with the part at the end of it. So there's kind of a few different things that go into it. It's the material development, it's sort of on its own thing. And then we can apply the material development characterization to each individual complex geometry or different manipulation of the part. So there's the material development, the software side, and then the actual welding.
And there's a lot that goes into it. And I imagine it's several programs because you also have the rotator or, the part that's the fixturing piece that's constantly, or the manipulator that's constantly moving back and forth and all around. And so you got to program that as well. Now, when you all program this, it's nothing like a cobot, right? You're probably using keyboard and a mouse and all that stuff, drawing it in I'm assuming a CAD CAM software. And then that later on it gets converted into a G code.
Mm-hmm. Yeah. So we actually have our own proprietary software called SculptPrint OS that actually started as a CNC machining software. So it's a voxel-based software where you kind of split your geometry into a bunch of little cubes, like 3D pixels. And it would start with whatever your stock was, create a tool path to cut away voxels until you end up with what you want. Essentially, what we did is just reverse that. So we start with nothing, kind of like building something with Legos. Mm-hmm. And then you add all your little voxels one bead at a time, one layer at a time until you end up with that geometry that you need. And that's what gets converted into the G code. So within that software, there's what we call a station file, but it's essentially a model of the entire system. So you see the floor plate, you see the positioner, the robot, the power source on the back. And then you can actually go through and analyze the path as it's being created. You can choose the torch angles, like Teresa was saying before. There's a lot of fancy stuff we can do with it, which is pretty exciting. And most of it we can sort of capture before we even send it to the robot. And it also goes with, so we do have 18 production cells, but we have a few different variations. So we have specific models to match each type of system that we would want to print in, which gives us a lot of capability for different types of parts we want to print, different geometries, things like that.
Now, in that software, does it kind of give you like a animated preview on, it'll kind of build the part for you? I know with the Torchmate, I can kind of hit like a cut preview, and it'll show me which cut profile it's going to take. Does it do something similar to that, where it actually kind of builds up that part into a 3D space, so you can kind of see which way the manipulator is going to move, which way the torch is going to go?
Yep. Yeah, exactly. You can actually, if you're just looking at the tool path itself, you can drag the robot through every single point of G-code that you want to see, and actually see what that's going to look like on the robot. You can see what the intended sort of print geometry is going to look like, so that as deposited based on how you're modeling it, comparing that back to the input part model. So sometimes we'll add additional stock or whatever for post-processing, machining, things like that. All of that is visualized in the software.
So that way you can figure out exactly where these parts need to be supported and all that. Because, I mean, like, especially if you're kind of branching out from the center mass, I mean, you've got to be able to support that in specific ways.
Yes.
Yeah, a lot of cases, that's where the manipulator comes in, because if you can turn the whole part, then you can build that in a vertical position, just build it up from there and use it. But the one thing Mandy didn't say, part of that material characterization. So you got to know your materials. And we work with a lot of different alloys. And each of these alloys wets out differently, just like when you're MIG welding normally.
Yeah.
And so you've got to understand and have that consistency, because now you've got a computer that is counting on it to wet out a certain way. And if it doesn't do that, you're in trouble. And so that's where it helps a lot to, know your filler metals, to, have something that's very, very, very consistent, so that it always wets out the same way.
Yeah, that's going to be difficult to kind of think that out, because I know like 308 runs completely different compared to like 70S6 versus like anything with nickel in it. It's almost like welding with mud. So how do you like tell the computer, hey, we're going to use this type of alloy, and so we're going to have to change some different variables because of the way the puddle wets or ties in?
Yeah, and even 308 versus 308 SI, properties are the same. They all meet a 308 composition, but the wetting is completely different. And that was part of what Mandy was talking about with the material characterization that you have to do up front before you ever get that first order for that material. You've got to understand exactly what it's going to do when you put that bead down.
Man, there's so many different variables wrapped up into that. Now, do you even have to worry about like heat input? I mean, as far as like, depending on the part geometry, like how fast can I actually go back over that bead before I start losing control and it just turns into a mass of molten metal on the floor?
Yeah, that's definitely a concern. Typically with the parts that are larger size, they sort of act as a heat sink. So it's not as much of a concern there. But once we start printing things that are a little bit smaller, have a thinner cross section, typically what we'll do is we'll monitor the inner pass temperature, like Teresa was saying. So we can do that on a per bead basis, just make sure the part gets below a certain threshold before applying or depositing more metal. Part of that goes into the qualification side of it as well. And then all of those welding parameters that we were sort of mentioning before, that also goes into it. The bead deposition, how you're placing your beads, has something to do with it as well. So that kind of goes more on the slicing side than the material development side. But heat input is definitely a hot term.
So when you're designing these things or laying them out, do you prefer stringers over weaves? Because I know that's a question a lot of people from the audience are going to want to know, because that's like the biggest welding debate is stringers versus weaves. Do you find that there's times it's beneficial to run a weave?
Yeah, absolutely.
Yeah, and the same part might have some short circuiting transfer, and it might have some spray transfer if it's a GMAW part. So depending on what part of the part you're at, you might want to do stringers, you might want to do weaves, you might want to short circuit, you might want to do spray transfer. And it just, for me, from a welding background, it's all so logical. It's just what you do if you had that torch in your hand. But the guys up front had to teach the software these things.
So you can, go ahead.
Oh, sorry. I was just going to say, I like to think about it on like a really basic level, as far as like if you're coloring in a picture, kind of like you go like kind of really fast and erratic throughout the center, and then you get nice and slow around the edges to make sure you don't go outside the lines. It's a very similar process, similar concept.
Kind of like shading it in.
Mm-hmm.
Okay. So you can actually change welding process or mode of metal transfer on the fly just through G-code.
Mm-hmm.
Okay. Yeah, I thought it was kind of neat when they rolled out the technology in the C300 that as you're welding, you can go from short circuit, and as long as your gas composition is right, you can double tap the trigger, and the next thing you know, you're into like a pulse or a pulse on pulse or a spray transfer. I thought that was kind of neat, and people were like, well, when are you going to use that? Well, if I'm working on different thicknesses of material and I'm all in the same part day in and day out, instead of doing all my flats, in short circuit because I got the thinner material down there, and then having to go over and switch the entire process over to go, vertical on a thicker piece, I can just double tap the trigger. And the machine's like, oh, okay, we're going to go from this process or this mode of metal transfer to a pulse spray transfer. So, okay, so it increases the wire feed speed, volts, and all that stuff. And as long as you have the right gas composition, the machine doesn't care.
Yeah, that's absolutely true. And when you start looking at some of these complex parts that are being built, that gives you a whole lot more flexibility to be able to do that. And I don't know if you want to talk about qualifications. Do you want to get that far?
Yeah, I want to dig, let's go deep into the rabbit hole, because that was one of the things that fascinated me during your presentation is you were like, okay, and then we're doing tensils on these things. We're doing Sharpie V-notch, fatigue testing, bend tests, how do you do that with additive manufacturing? So I thought that was kind of cool how you guys kind of set up these billets of material based off the process, the filler metal, the gas comp. I mean, because you have to, at the end of the day, the part still has to be serviceable. And once it's completed, it has to be inspected. Well, what are we inspecting it to? So yeah, if you could kind of, go dive deep all in on, how to qualify this stuff, all the processes and procedures that go along with it.
Okay. So, we're talking about, building these parts and changing from spray to short circuit, or changing from weave to stringer, or running faster or slower and changing the heat input. Well, we want that flexibility because we need it to be able to build these complex shapes. But there's not a lot of welding codes that let you do that, plus or minus 10% on this. So we took a page out of this is the code community, ASME 9, D codes, API is going this way too. But we took a page out of the seismic and the bridge and the military qualifications, where they require that you qualify the lowest cooling rate, which is a combination of the lowest heat input with the lowest interpass temperature. You qualify the highest, the lowest cooling rate, which is the highest heat input with the highest interpass temperature. And you qualify that for spray transfer and for short circuit transfer. So one qualification is an absolute minimum of 4 blocks. And most qualifications are 8 blocks, because you want that flexibility when you start building that to be able to make those changes. And each of these qualification blocks is an additive build. And you take pencils, bend specimens, Sharpies out of there, chemical composition. But then it gives you the flexibility to build anywhere within that bounding box.
So essentially, you literally create the weld coupon out of weld metal.
Yep, exactly.
So now what sizes are you typically doing this? Because I know like everybody's familiar with, okay, if we're going to test to D11, it's a 6-inch plate, 6 by 3 inch coupons. We're going to do a V groove, whatever the case may be. But if we're doing a procedure qualification, okay, now the coupons are 20 inches. But how do you figure out how big your specimens need to be? Because once you get done welding it out, you've got to machine it down to pull your Sharpies out, your bend test, your fatigue tests, all that stuff.
Yeah, and some of them are quite large. So if you also, what I didn't mention is you do the highest and lowest cooling rates for the different processes. We also do your thinnest and thickest wall section. So
for pipe, yeah.
Yeah, so you are doing qualifications. So if you're building something that's got a big fat part to it and also a skinny part to it, you do qualifications both ways. And, to make sure that you're not getting any of that base plate, because you have to start building on something. So you got a base plate there. You have to be at least 2 inches away from there before you start taking your specimens out. So it's, the qualifications aren't trivial. They're pretty complex, pretty costly, but then they give you the flexibility you need to do what you want when you're building it.
So it kind of opens up the doors a little bit more as to, okay, on this G code path, we can go ahead and essentially double tap the trigger, go into a different mode of metal transfer, really pour the coals to it. And then once we get up to this area, we're going to back it off. So that way that entire range is covered within there, because those are all essential variables. Everything that you have to weld through, and every time you change something, your heat input's now an essential variable. Your mode of metal transfer is an essential variable. Depending on how far you go out of your voltage and amps, that becomes a new essential variable. So, you've got, I want to see what one of these WPSs or PQRs look like, because it's got to be hundreds of pages to do this stuff.
Yeah, so we've been using C-Spec software to do our WPSs, and so it's set up for normal WPSs, normal joining or overlay WPSs. So not only do we have 8 of them that are combined to be one big PQR qualification packet, there are a lot of little notes on there. Because when you're doing this, you not only have all of the same essential variables that you had before, but you have a few ones that are combination, like the highest heat input and the highest cooling rate. So there's a lot of notes on these PQRs. They're not real clean at this point.
I got you. Yeah, C-Spec's got to make it a whole heck of a lot easier. That's the software I'm anticipating on using in the near future. Because I do PQR development and all that stuff, and it's man, I'm tired of using Excel.
Oh, let me tell you,
it's a game changer. Dustin gave me the demo, and I was like, man, where's this been all my life?
Yes. Once you get to a certain number of PQRs, ditch the Excel.
Now, are you all able to use or repurpose some of the WPSs and PQRs that you've developed? Okay, we were able to build this flower pot, but it's essentially the same chemistry and configuration as this boat prop we're going to use over here. So can you go ahead and just reutilize a WPS and a PQR that you've already done? Or does it have to be specific for each part that you're building?
So typically the way we handle it is that it's specific per material and per what we call weld recipe. So the collection of the parameters for, say, different size beads, different types of beads that we want to be using. We call them infill versus perimeter, like I was mentioning before with the coloring page. But typically, once you qualify a specific weld recipe, if you can use it in any part geometry you want to, as long as your essential variables stay within the bracketed qualification.
So that's, it's a very onerous, complicated qualification process. But then, you can take that and you can build flower pots and boat propellers and hydraulic shafts from the same one without requalifying. You'd have to write a new WPS usually, but you don't have to go back and requalify.
Because you got all the information from the PQR, you can just kind of pick and choose what you need to build that recipe, essentially.
Exactly.
Now, are the code committees getting involved in writing new codes and standards specifically for additive manufacturing, or are they just kind of, they're just going to put a new clause out in D11 for, if you're building bridge components, or, we're going to throw something to D12 for aluminum, or is there going to be a specific D1 for robotic or additive manufacturing?
Yeah, so there is actually D20, and D20 was probably the first code that came out that was specifically additive manufacturing. It addressed, and that's AWS D20. It addressed laser powder bed fusion. It addressed a lot of different types of additive manufacturing. After about 5 years of using it, it was recognized that it really doesn't make sense. You can't, it's like mixing apples and oranges when you're talking about powder bed fusion and that sort of process and welding. So now it's being split into two. So there will be a D20.1 for the powder processes and a D20.2 for the wire-based processes. API has 20S, which is standard for building API type parts. And they're in that exact same process of splitting it apart into two, because it sounded good at first, but it really doesn't make sense. ASME Section 9, as of July 1st, so hot off the press, has a new section in Section 9, QW600. QW600 is how to qualify additive welding procedures. And all three of those codes, the AWS D20, the API 20S, and ASME Section 9, are going with the same bracketed qualification approach. I can't promise anything with AWS and API because those haven't finished balloting.
Yeah,
but
they don't get along too well sometimes.
Yeah, no, it looks like everybody's going in the same direction, which is great for industry, because then, whether you're building header pipes for a power plant, or you're building something that goes into a building or a bridge, or a pressure vessel, you can use that same qualification approach.
All right, we're going to go ahead and take a quick commercial break. This segment of the Arc Junkies podcast is brought to you by Strong Hand Tools. Educators, are you struggling to get quality fabrication tools in your shop to implement project-based learning? I'm sure you are. I've been there myself. Luckily, Strong Hand Tools is still sending out their educational packs to help alleviate this burden. Just go to stronghandtools.com/ArcJunkies and sign up for their educational discount program. Not only are you going to get some awesome discounts and promos for purchasing tools for your school, but you can also get a free toolkit just for signing up. Head on over to stronghandtools.com/ArcJunkies to sign up today. We're also brought to you by Everlast Welders. Are you looking to start your welding journey on a limited budget, but still want access to the features and functions of other high-dollar machines? Then check out Everlast Welders. They have a machine for every budget and skill level, like their all-new Everlast Typhoon. You can pick up this new machine with industry-first waveforms for AC TIG welding right now for just $27.49 and get free shipping right to your door. And as always, when you buy any machine that comes with a stock foot pedal, you can type Arc Junkies in the comment section at checkout and get that free Nova foot pedal and TIG torch upgrade. Everlast Welders. Weld mean, weld green. Now let's get back to the show. Yeah, one of the things I thought that was kind of neat with that whole process is building. You can essentially 3D print a TYK connection. I thought that was kind of like my favorite part of your whole presentation, because I was like, man, that's like groundbreaking right there. I mean, case in point, the roller coaster that just failed the other day. I don't know if you all seen that, but I mean, like if you are able to 3D print the TYK connection, because you've got such that skewed T-joint where you really can't get adequate penetration and all that. If you're able to 3D print that, the whole thing is completely solid. You machine it out and you're left with maybe like a 1G, a 5G, or a 6G weldment out in the field, which everybody's pretty familiar with that.
Yeah, and that's one of my favorites too, because I know how hard. I mean, this to do a good job welding one of those, you have to be in the top 5% of welders. And I've had to analyze a lot of failures in that area, because it's just so easy to get defects. And the idea of being able to move that joint that has to be welded in the field out onto just a straight section of pipe where somebody can go in and weld. I think this is going to be a real big advantage for the field welders as well, just making their jobs a whole lot easier. You won't have to be, crawling around on the ground trying to get to those. So the other thing that does is, in power plants, you've got the hot areas, and you can move the joints out of the hot areas. So those heat affected zones and those stresses that you get from field joining aren't really affecting it the way they used to be. I'm really excited about just how to integrate this into into facilities to really help in the safety.
Yeah, I thought it was kind of like a neat way, a neat solution to be able to develop that. You build that, and it's kind of like kind of ordering a 90 for handrail or something like that. You're like, yeah, I need a TYK connection for some 6-inch Schedule 80, and here's the angles that I need to hit. And the welders out in the field, they're just connecting the 90-degree ends, and you guys can probably get them pre-beveled and everything. I mean, it's already set. You just put your spacers in there, tack it up, and weld it out.
Yep. And you know it's going to be round, and all those things that you have to deal with as a welder out in the field. It should really make their jobs a whole lot easier.
Well, you guys are going to have to manufacture or add some sort of flaw in the design, because pipes, as well as I do, pipes never really 100% round. You got to kind of fight it to get it in there. So if you build it perfect, it's not going to match up all the way around.
Absolutely.
Okay. Now, Teresa, when I was when we were at the AISC convention, one of the things I wanted to ask you about was using some of the newer advanced processes that Lincoln has. So like your Rapid Arc, your Rapid X, Hyperfill, that's coming on board. That's a really cool, system that's being ran. Are you all incorporating a lot of those advanced processes and new techniques into additive manufacturing?
Absolutely. They have waveforms of their own. They use all sorts. That's why we can do things that others can't, because we've got these machine designers, we've got the software developers, the waveform developers, so that we can do things with the pulsing characteristics and things like that make that nickel metal not feel so much like bubble gum, and get it to wet out a little bit better. So yeah, we're all over those new waveforms. You guys never use standard old spray, even though I said, yeah.
Kind of old school stuff. You're like, no, we got this new stuff over here called Rapid Arc. We can run at 800 linear inches per minute.
Right.
Yeah, that stuff is crazy.
So the conference was a bridge conference, and we did talk a lot about fatigue and about these welded connections, and the whole idea of being able to put these welded connections. And the other thing that's cool that you can do with this is, the parts can look like something. It's weld metal. So if you want to spell out somebody's name in the middle of it, or you want to, have something unique or a bit artistic, there's an entire sculpture that went in. What was that made out of, Mandy?
316 LSI.
316 stainless, and it looks like I don't know, 30-foot tall heart valves in front of a medical facility that an artist did, and Lincoln printed up for them in the additive facility. But
yes, that one is one of my favorite projects. It was, like she said, kind of like a large heart valve, almost like a Y shape. But it was a large tube, so it was a single bead tube. What I like to highlight about is, yes, it's like 30 feet tall. So we printed it in, I think, 9 different pieces. But because of the amount of systems we had, we printed them all simultaneously. And I think it was like 4,000 pounds of stainless steel deposited. We did it in 7 days. And of course, they were all joined somewhere else later on. But it's just statistically, it feels pretty good. Definitely challenging, but very, very cool project.
Yeah, I mean, I didn't even think about the whole artistic aspect. I figured you guys would be booked building, different parts and pieces and stuff that they just don't make anymore. Like you were saying, it works really good for different castings because that process takes so long. It's very expensive and time consuming.
So we had one that I may have shown this at the AISC. There was a piece of equipment, and the maintenance guy recognized that there was some vibration that shouldn't be there. So when he got in and started inspecting, he saw there was a cracked flange. So I pulled it out, said, okay, I need a new one of these. But it was a pre-World War II part. It was a steel casting with a couple flanges welded to it, and he didn't have a print for it. So I sent it over, and the additive facility, one of the other cool things they have is the 3D scanners. So they took and scanned that to make a 3D print from it and built it, machined the parts that needed to be machined. And I think it was less than a week they had it back in service. So
wow.
there's, replacement parts, obsolete replacement parts, and the whole parts inventory thing is just huge here.
Yeah, I wanted to talk about that. The 3D scanner, it kind of looks like a dodecahedron with a laser on the front of it. And so you're able to bring in a part or a piece and say, hey, I need one of these. And instead of having to reverse engineer it and put it into redraw it in a CAD CAM software, you just take that little piece and kind of move it back and forth over the object, and it does an entire 3D rendering.
Mm-hmm. Yeah, exactly. So we've used it like in that situation where we actually use it to create a model to print to. But more often we actually use it as a quality assurance tool. If you can imagine, we're printing lots of really complex sort of organic shapes. And they're pretty big. You can't quite take calipers up to it. So being able to capture the entire part and all of the features of that part, and then be able to verify all of those features in the software is huge from a dimensional verification perspective. But the way it kind of works is that it kind of looks like a soccer ball, I guess. Essentially, that's shooting a laser grid onto the part, and it's collecting a point cloud and then fitting a mesh to that point cloud. And that's where we get the 3D model from. The resolution is pretty crazy. So if you can imagine seeing our surface finish, it's not quite pristine, but you can see the individual layers. They're weld beads. But we can see all of those individual, I don't want to call them imperfections, but you can sort of see the sort of scalloped edge of our surface finish in those meshes. So I love 3D scanning. I think it's so cool. Just watching it kind of create the model in the software as you're capturing it is really cool. And it's a very useful tool for us.
Well, it sounds like it. Not only can you come up with an entirely new part, but like you said, you can go back and do like a QA, QC after the fact and say, hey, is what we designed what we actually got, once it finally ran its last pass?
Yeah, exactly.
And you all know about, distortion that you get when you're welding. So that's the software has distortion figured into it. But, things don't always turn out the way you expect. So sometimes they'll pull this up on a hot part that, they're in the middle of making just to make sure that things are still as we expected. So, it's a great tool from a quality assurance standpoint.
Yeah. Now, Mandy, going back to what you were saying earlier about like the kind of scalloped edges, or you can kind of see where the different weld layers are, you all are able to, once that part's complete, say, okay, this area needs to have like a smooth finish or something like that. So you can always take that over to like a machine shop, or you can dress it up with a grinder or whatever the case may be to get the actual final finish or final look or final fit that you need post welding, right?
Mm-hmm. Yeah, exactly. It's all, each part is unique and has different requirements. We can do it where we add that additional stock planning for machining to an entire part. We could do it for only specific features, say only one area of it is fitting into an assembly, and leave that sort of as printed surface on other areas of the part. But yeah, we definitely plan for post-processing for a lot of the parts. It just depends on what the end use is, what the requirements are from the customer. But a lot of that happens just in the same software, adding that extra stock. And then something that's cool about the scanning as well is when we bring in the scan of the final completed print geometry, we can not only compare it to what we expected to print, but we can also compare it to that net model. So, Teresa mentioned a little bit of distortion. Sometimes they move a little bit. So being able to verify that the final part sort of sits within the printed part, that's a big part of what we do in the QA stage as well.
Okay. So we've talked about how cool this stuff is. What are some of the disadvantages to additive manufacturing?
Yeah. So each time somebody, comes in with a part and says, either I can't source this, or I want to design it a little differently, or it costs a lot to have it forged. you have to look at cost and benefit, because, if you're doing a casting, if you already have a casting form there and all you're doing is pouring metal into a casting, it's going to be a lot cheaper than it is to actually weld this and create, because we have to start with weld wire, we have to weld it up. So, there's that cost side of it. You have to always decide. There are some things that you might want to do that you can't cast, like the hollow bladed propeller or different shapes. So, those are advantages, but you can't, it's not everything to everyone. It sounds really cool. If you're doing really small parts, you can do really good features and have very tiny little parts that come off of it that will be perfect. But if you're doing something out of weld metal, it's got to be big, and it doesn't have that same dimensional accuracy and surface finish unless you're going to grind it. So yeah, it's there's when you look especially at parts that are existing, sometimes it doesn't make sense. Sometimes from a cost standpoint, it doesn't make sense. Sometimes from just a procedural standpoint. It's usually a time savings because castings and forgings take so long to get these large castings and forgings we're talking about. We can do some things with mechanical properties that you can't do with a casting or forging. So that's a benefit. But yeah, I think once the designers start thinking outside the box, because they still think about pipes being round, because that's the way they're made today. But there's no reason your pipe has to be round. There's no reason your TKY joint has to have a tight angle there. If you put a little radius on it, you've all of a sudden got much better fatigue properties. You've got more material at the high stress points, and that's where this stuff really shines.
Yeah, I mean, because you can, like you said, dial in your own recipe. I mean, creating a radius just in like that little spider web where they kind of meet up. You're going to put more material in there and be able to distribute any incurring loads a lot better.
Yeah, and sometimes it's putting more material in to distribute the load or take care of specific fatigue issues. But sometimes it's putting less material in, because if you think about a forging and a casting, you're kind of stuck with one wall thickness, where what we can do is vary the wall thickness based on the load. So you can thin up certain parts where it's really not carrying much of a load, and you can get a pretty significant weight save. The guys in aviation have figured this out, and that's one of the things that's making the aircraft a whole lot more efficient, is these designs for additive, where you put the material where it needs to be. But it's really hard, I think. I'm kind of waiting for the next generation, because, my generation still thinks about the way things have always looked. And you have to think in a completely different way to get the advantages of this process.
Yeah, you kind of do need to bring in the younger generation, because like you said, like, that's the way we've always done it. We've done it like this for 20 years. Why do we need to change it now? It's always worked for us. It's like, well, there's a better way. That's why we're coming out with new modes of metal transfer, because nobody really wants to do short circuit anymore. But that's really neat thinking about aviation. You're putting the mass where it's actually needed. I mean, you can, bring, significant weight weight reductions into the system, but still not lose any strength or fatigue throughout, where you actually need it. Like, the wings, you kind of taper it back through the fuselage and all that, where you don't need a whole lot of weight, except for where specific components are going to be. Then you can beef those areas up and kind of lighten the load in some of the other areas.
Yeah. And, most of our customers won't let us talk about them specifically, but the ones that are the most fun are the ones where the designers have an open mind and creativity and say, well, can you do this? And why do we have that metal there? Or do we need that? Or we're always seeing cracks in this area. What can we do to eliminate that? And that's where it really shines. That's where you can do things that you can't do any other way, sometimes with less material, and really make it a safer component.
Now, because I'm sure many folks in the audience have done this before, when you're using the gas metal arc welding process, tips burn up. Weld wire has some feeding issues sometimes. What happens when you're on, G code line, 7,916, and all of a sudden that weld wire gets pinned in the contact tip? Does the machine stop or?
Yeah, so there's a lot of stuff that's sort of programmed into it. We have a pretty, I'll say, sophisticated foreground code on the robots. They're pretty smart. They do exactly what you tell them to do, but they're pretty smart. So if something happens that's unexpected, so we call like an unplanned intervention, like a burn back, like you mentioned, or a tangled drum or something, the robot will alarm for help from one of our operators. So we do have 24/7 production support through sort of automatic welding operators, as well as engineering support. So those are typically situations where the operator would approach the cell. Typically it has like a very helpful message of, this is the problem I'm having, can you please help me? There's also things like we do go through contact tips, and there are sort of planned interventions like changing out spools or drums or contact tips. So many contact tips. And in those situations, it happens based on, say, like a weight deposition, or there's a sensor that tells you, hey, you're getting close to the end of this wired drum. And in that case, it also alarms for the operator to come over and help. And then we sort of keep like what we call operator logs. So all of the intervention, planned or unplanned, all gets reported based on a layer and bead basis. So we can go back if we need to figure out what happened in a certain part. Say we're doing testing later on. But all of that is very traceable, and it's very useful information. But it's definitely not perfect. It's not 100% welding all the time. Typically, I think we try to like aim for 90% efficiency. So when I say efficiency, I mean 90% of the time the arc is on. So the other 10% of the time is changing out contact tips, just air moves between beads. It's not all one continuous weld, things like that. But it's pretty automated, but there's definitely a little bit of human help every once in a while.
Okay.
Yeah, you hear people talk about running their factories lights out, where you can go home at 5 o'clock and come back at 5 in the morning. That's not something we think is a good idea, at least not at this point.
Yeah, you come back into the shop the next morning and the machines have just gone haywire.
Yep.
Yeah, you don't want to walk in on that.
Yeah.
Well, especially, with a robot moving back and forth and everything, playing with weld wire, and, that just sounds like disaster.
Yep.
Now, have y'all done a whole lot with, like, aluminum additive manufacturing, or has it been primarily, like, nickels and steels? Because I imagine aluminum's, it's a different animal to work with, just because of heat input, and, we already talked about burning back contact tips. That happens pretty frequently with aluminum MIG welding.
Yeah, so aluminum is a different animal. So I think kind of the different metals type, nickel alloys, stainless steels, low alloy steels, and mild steels. I guess that's 6 of them. Yeah. So of those, we are not commercially doing any aluminum or titanium. There is some with the titanium. It's really tricky, and there's some different reasons why we don't want to do that. Even the industries that it's being used in. And aluminum, could we do it? Yeah. But if we can keep our robots busy on other stuff right now, I think we're happy to do that, because there's a lot going on with aluminum.
Yeah, that makes sense. Aluminum's pretty frustrating to begin with sometimes.
Yeah.
Now, is the software, the technology, the equipment, is that stuff that's commercially available, or is additive manufacturing something that Lincoln, for the most part, they're just providing that service?
So from Lincoln's standpoint, Lincoln is not selling any additive manufacturing cells that you can put somewhere. That's, I think we want to be able to walk before we run. And so right now we're building parts for people. That doesn't say that the business strategy is not going to change in the future, and we're not going to, put a cell at somebody's shop in Houston where they, have all kinds of spare parts that they want to be able to print all the time. But right now we are almost exclusively printing parts. There are some universities and research organizations that we partner with, Oak Ridge and a few of the universities, where we do put our cells in there.
Okay. Yeah, I was just wondering because I haven't seen it commercially available. I know FabTech's coming up. I wasn't sure if you guys would be doing demos at FabTech or anything like that, trying to push and move equipment to be able to do additive manufacturing.
Yeah, and you'll see, I mean, there are people out there that have that business model where they want to build cells and ship them to people and have people use them. I think at this point in time, we care too much about welding to do that. We want to make sure that, first, the worst thing you can do in any industry is have a bad name, have a failure. So we don't want to see any failures. And that's one of the reasons we spend so much time on these codes and standards, because we want to make sure that this is done in a safe way, whether it's done by Lincoln or by somebody else, because we want people to keep welding.
Mm-hmm. Now, I know you work with a lot of clients that want to remain anonymous, or they've got proprietary pieces and stuff that's being built. But what's one of the coolest pieces that you guys have been able to build in your facility that you can talk about?
So I don't know.
See you lighting up over there.
Okay, so she may have a different one, but my favorite is, just because I'm kind of a nerd and this is right up my alley, is Chevron came in and they had a facility that was down. And you can imagine, you think refinery type facilities, downtime is not a good thing.
Millions of dollars per hour.
Yeah. And they found that that they had some parts that had to be replaced, and Lincoln built those, and again, built them on a number of different cells so we could build them all simultaneously, put them back into service. And Chevron was excited enough about the prospect, not just the low downtime, but what else they could do with this, that they actually went public with this. And so, you can Google Chevron, additive, I don't know, Lincoln, and then it'll come up and tell the whole story. But these were high temperature, 1500 degree Fahrenheit parts. They were pressure retaining parts. So it's a really cool application. And to know that we can help with these situations and work with the designers and work with the companies to make sure we get them up and running, but in a very, very safe manner.
I mentioned before, I think my favorite is the sculpture because I like the artsy stuff. But from a impressive project perspective, Chevron definitely, I would agree with Teresa. The thing that she didn't mention is we also had to qualify those parts to ASME. So not only did we get part models, we had to get wire very quickly. It was a lot of wire to go through. We were depositing metal, we were making parts, but we were also printing test coupons to go get qualified. And it was a huge effort on our engineering team, and it definitely paid off, I think, for everybody.
Now, do y'all have different cells that kind of work in production and then a different set of cells just for developing PQRs?
Typically we use kind of the same ones. It's sort of based on availability at this point. So we do have, I mentioned we have 18 production cells right now. There's a few different variations, mostly because we keep outgrowing ourselves. So some of the systems are modified to have either risers underneath the robot so we can reach a bit taller, or larger build plates so we can reach a bit further. But typically it's based on availability. What are we printing at the time? We'll usually just sort of dedicate a certain number of cells to get through those PQR coupons. Because typically it's like a fast timeline when we want to do that kind of stuff. But of the 18, usually like there's at least 2 or 3 that are doing some type of development, some type of qualification work at a time.
Okay. Now, how far do you think we're off, like time-wise, just in general, from 3D printing buildings? Because we already talked earlier about 3D printing, concrete. I know they did that at a military barracks. They did the whole concrete layout and everything. But some structures have to have structural steel internally. How far are we off? Because everybody's going to be like, well, why would I want to get into welding if these robots and this additive manufacturing stuff is going to take over? How far do you think we're away from, 3D printing structural steel buildings?
I don't think that anything we're doing is going to replace welders. Because of all of the different, not only, engineering requirements that go into it, but also, you don't necessarily want a completely rigid structure. And if it's all weld metal, it's a rigid structure. Mm-hmm. And doing these, there's certainly some benefit. There was a bridge built in the Netherlands.
Yeah.
All out there. And, you can do that, but is it practical? Probably not. And, it's a great showpiece and it's really cool to talk about. But I think, the way I see it is we're going to certainly make the jobs of welders a little bit easier. We might be able to reduce the number of welded joints by building transition pieces, but the likelihood of building an entire structure, I would say is, certainly not in my lifetime. I'm not sure it's in Mandy's lifetime even.
Probably not.
Well, that's good to hear. The audience can be happy about that. Well, Teresa, Mandy, it's been a pleasure having you all on the show. Where can people go to find more information on additive manufacturing or some of the cool stuff you all are doing at Lincoln?
So, the Lincoln website, lincolnelectric.com/additive. Is that right?
Yeah.
Okay. Yeah. Yes. And it's really great fun. There's a lot of videos. You can also look on YouTube and you'll see some of these videos that we were talking about.
Yeah, I'll link the video you sent me with the 3D printer. I'll link that in the show notes so people can click on that and check it out. I thought that was pretty neat.
Yeah, isn't that cool? Yeah.
Well, great. Again, thank you all so much for coming out and kind of educating us on the additive manufacturing process and some of its capabilities.
Yeah, thank you.
Thank you.
All right, ladies and gents, thank you so much for tuning into today's episode. I hope y'all enjoyed hearing about this emerging technology in our industry. For more information on this process, you can head on over to lincolnelectric.com or you can check out their YouTube channel as well. Hope you all have a great rest of your week. Stay safe out there, and until next time, make every weld better than your last.